Hi there. In this video, we're going to be looking at stationary points, that is maximum and minimum of multivariable functions. It's a very important application of multivariable calculus. In the real world, we are always wanting to find maximum and minimum of something. If we think about in the business environment, we're always wanting to minimize costs and maximize profits. If we think about engineering, if we think about a tank, what we're wanting to do is maximize the volume of the tank, but minimize the surface area of the tank for different reasons. So it's always about finding maximum and minimum of something. And there's a specific procedure that we can follow to determine the maximum and minimum. In multivariable calculus, it's a bit more complex because we can have what's called the global maximum and the global minimum, and the local maximum and the local minimum. So what that means is, if you picture a mountain range, the Himalayas, for example, there's many mountains, but Mount Everest is the highest. So there's one point that's the true maximum, and there's one point that's the true minimum. Or it could be either one of those. It could either have a maximum or a minimum, depending on the type of function that it is. So starting off with single variable calculus as a quick revision. If we have the x and y axis, and we have a random curve, we have 2 points A and B. x1 corresponds to the maximum at A, and x2 corresponds to the minimum at B. So what's true in both these instances at A and B is that the derivative dy dx, that's the first derivative, is equal to 0. So how y changes with x is 0. The tangent to the point is 0. So the tangent is just a vertical line at both A and B. So by finding the derivative and setting it to equal to 0, we're able to determine, yes, that there is a turning point, that it's a stationary point, as it's called. So how do we determine if it's a maximum or a minimum? Well, at A, we know it's a maximum because the second derivative is less than 0. And at B, we know it's a minimum because the second derivative is greater than or equal to 0. Why is this the case? Well, we can just imagine a simple illustration of a ball that's thrown into the air. We could have y as its vertical position and t the time taken. So at time 0, we throw the ball up in the air with some initial speed, and it travels, it goes up, it reaches some maximum height, and it comes away all back down, hits the ground again, and maybe bounces and then carries on like that. So what's happening here? What's happening is that at its maximum height, of course, that would correspond to its speed or its velocity that's equal to 0. So the ball stops. If we take a snapshot at this point, the ball is literally stationary. So it's a stationary point. So how do we know it's a maximum? What does that have to do with the second derivative? Well, the second derivative in this example corresponds to acceleration. Well, gravitational acceleration specifically. When we throw up the ball in the air with this initial speed, we see that the speed is reducing as it's traveling up until it's 0. So it has some initial speed when it's thrown, and it goes down until it becomes 0 at its maximum height. So the speed is reducing. In other words, it's decelerating. So the second derivative at this point is actually less than 0. It's decelerating. And then as it comes back down, what's going on? Its speed starts increasing. And in other words, it's accelerating. And then when it hits the ground, it's at a maximum acceleration. So the second derivative at the minimum point is actually greater than 0. So this is just a natural phenomenon. It's just a way of illustrating that our second derivatives is an indicator of whether it's a maximum or a minimum. This point is important in a different context in multivariable calculus. On the left-hand side, we have this little bell-shaped curve, or you can think of it that way. And at point P, we see that we have a maximum. On the right-hand side, we have the same surface inverted, and we see that point P corresponds to a minimum. So at both graphs, the x value is A and the y value is B. So this is the coordinates A and B that corresponds to the maximum year and the minimum year. So the way to think about this is if we take a random point nearby P. So that would be point Q. So Q is in the vicinity of P. So it's some h distance away from the x coordinate and some k distance away from the y coordinate. So if P is a maximum and Q is a point nearby, P will always be bigger than Q. This makes sense because P is a maximum. Maximum literally means that it is the biggest value. So anything nearby would be smaller than it. So let's write this down in terms of an expression. If we have some point that's nearby, that would be point Q, and it is some h distance away from the x coordinate and k distance away from the y coordinate, and then we subtract point P, this should be less than equal to 0. This would make sense because point P is bigger than point Q. This is point P being bigger than point Q. So we have a smaller number minus a bigger number that would be less than equal to 0. And this scenario corresponds to a maximum value. So the same analysis is applied to the graph on the right-hand side. We have a point P, point Q is nearby. Since Q is a minimum, it's the smallest value, Q would always be bigger than P. So writing that down, we have point Q. Again, we're subtracting it from point P, and we see that this should be greater than equal to 0. And this would correspond to a minimum. In this instance, we have a bigger number subtracted by a smaller number. That's why we get it greater than 0. Sorry. In single variable calculus, we saw that the first derivative corresponded to the tangent line, and this tangent line we saw is actually parallel to the x-axis. I've drawn it quite poorly here. Let me just draw it a bit better anyway. We see that this tangent line is actually horizontal to the x-axis, and that means that its gradient is 0. So at this maximum or minimum point, instead of a tangent line, what we have is a tangent plane. And the only way that this tangent plane would be a minimum, or rather parallel to the xy plane. Remember, the xy plane forms the base. And if we imagine we draw the base on top of this point P, you could see that it's parallel to it. So we think of a plate that's parallel to the xy plane, and that would correspond to the scenario where the first derivative with respect to x is equal to 0, and the derivative with respect to y is also equal to 0. So just as it was the case where dy dx is equal to 0, it's also the case in multivariable calculus where the derivatives with respect to all variables is equal to 0. So that's our starting point. So now our question is, how do we know if something is truly a maximum or truly a minimum? If we have our graph and we determine our derivatives, we can find stationary points. But how do we know if there is really a minimum or a maximum point at whatever point we are considering? If we can think of the mountain range example that we looked at earlier, we could find the stationary points at the tips of each of those mountains, the peak. We could find stationary points at each of the peaks. But how would we determine that actually Mount Everest is actually the true maximum value? It's the truly biggest mountain. How would we determine that? So we need a method to find the global maximum, the global minimum, or the global minimum. And what we're going to go through next is the technique of determining that. The way we'll go about doing it is writing the Taylor series for a point that's nearby the local maximum, or sorry, the maximum or the minimum. So in other words, writing the Taylor series for point Q. So it's f a plus h b plus k. And this is equal to the function value at the maximum or the minimum. That's at point P. So it would be f at AB. And then plus h times day f dx plus k times day f dy. If you need to revise the Taylor series, It's done so in a previous video. You're more than welcome to go and have a look at it. So then we look at the second order derivatives. So it starts off with 1 over 2 factorial all into h squared times the second derivative with respect to x. And remember, we have two mixed partials, so we have to have a 2 in front there because it's 2 of them. And then we have h times k, and of course the second derivative with respect to both variables. And then lastly, k squared times the second derivative with respect to y. And we'll have higher order terms. So we will neglect these higher order terms because it can be done so in this illustration. So we're going to take this FAB to the other side. We want to end up with this expression. So we have FA plus H B plus K, and then taking this over to the other side, minus F at AB, and this is equal to everything on the right hand side. However, we can do some simplifications here, or rather certain terms go to 0. We see that at the maximum and minimum, the first derivatives with both respect to x and y are equal to 0. So in other words, this term is equal to 0 and that term is also equal to 0. So what we're left with is this part of the expression. And this is an important part of the expression. It's what we're going to use to actually determine if something is a true maximum or a true minimum. And you might wonder at this stage, how are we going to do that? Well, we're going to do a manipulation, a mathematical or algebraic manipulation of this expression that will enable us to find it. So we're going to ignore this 1 over 2 factorial because we're more interested in the signs of the derivatives. That's what's really going to influence our analysis. So we won't consider it at this stage. So the first thing that we're going to do is we're going to take out a common factor from this part of the expression. And that common factor is 1 over the second derivative with respect to x. So why we're doing this will become abundantly clear just now, but we're taking this expression and we're taking out from it 1 over the second derivative with respect to x. So when we do that, we have to rearrange this term in a particular manner. And what happens is that we have h times df squared dx squared plus k second derivative with respect to x and y. And this term is squared. So if we think about it like this, we have h squared, and this corresponds to this h squared. Then we have the second derivative squared. So that will cancel out with this second derivative being in the denominator in front of the expression. And what we'll be left with is df squared here. Then 2 times h times the second derivative with respect to x, which will cancel out again with this, times k times the mixed partials. So that will correspond to the second term in the expression on the left-hand side. However, there is a last term, which would be the second derivative, the mixed partial squared. And that is not in this expression on the left-hand side. So we would need to subtract it out from the right-hand side. But before we do that, we see that we have k squared day squared f day y on the left-hand side. So we need to also include this term on the right-hand side. So the way we'll do it is that we will add k squared. So this will correspond to this k squared. And in brackets, of course, we now need to cancel off this second derivative in the denominator. So we would write day squared f dx squared, which will cancel off with this. And what we're left with is this expression with respect to y, sorry, this second derivative with respect to y. So that's day squared f day y squared. And remember earlier I had mentioned that when we square this last term, we'll have this mixed partial squared. So we need to subtract that out of this equation. So we're going to have that k squared, and this will correspond to this k squared here. So we'll say minus this mixed partial squared. I'll just zoom out so it can be made visible. So it is day f squared, day x, day y squared. And we close the bracket like that. So we have a fairly complicated looking expression here, and it's not really important for us. We need to keep sight of what we want. What we want is to determine what is the true maximum and the true minimum. Which mountain is truly Mount Everest? That is the question that we're trying to answer just by determining the stationary points. And the way we do it is that we start analyzing this expression on the right-hand side. The signs of the derivatives, second derivative specifically, will enable us to determine whether it's a true maximum or a true minimum. Firstly, look at the first term in this expression on the right-hand side. Whatever the derivatives are, they are going to be squared. So regardless of what happens, this first term will be a positive number. That's the first thing to notice. Now we go on to the second term. We see that we have day squared f with respect to x and day squared f with respect to y. And we have this mixed partial also here on the right-hand side. So if we want to determine the true maximum or the true minimum, this entire expression on the right-hand side needs to be an extreme value. It needs to be either the most positive number that it can be or the most negative number that it can possibly be. So this is very important to note. So how can we make it the most positive number or the most negative number? We can make it the most positive number by this first term being positive, which it obviously will be all the time, and this second term being positive as well. And of course, this first derivative also being positive. So if this is positive and this is positive, and the first derivative is positive, then we would have maximized this entire expression. So how else now can we get the most negative number, the most negative value? Well, we can have the most negative value if firstly the term within the square brackets is also a positive number and this first derivative is a negative number. What would happen if this second term was a negative? Well, we would have a positive number, then we would take away something from that positive number that will give us a smaller number. And then the sign is determined by the derivative in front of the square brackets. So in this case here, we wouldn't get the biggest value or the smallest possible value. So this is illustrating the point that both of these terms within the square bracket must be positive numbers. So the second term here, for this second term to be a positive number, we see that both the second derivative with respect to x and the second derivative with respect to y, both of them should be of the same sign. If both are positive, then this entire second term would be a positive number, which is what we want. And if both are negative, then it would still be a positive number. But now we would have a negative derivative here, so it would become the extreme minimum. So that's a very important point. So in other words, in order to find the true maximum or the true minimum, so the true maximum or the true minimum is established, or we're able to determine it when this second part of this term is positive. So that is when day squared f day x squared times day f squared day y squared is greater than day squared f day x day y. So that is a very, very important point to establish inside this entire, I forgot about the square here. Well, another way of writing this is if day squared f day x squared times day squared f with respect to y minus the mixed partial is greater than 0. This is a very important point. Perhaps it's the first important point. So the second important point is that both of these things need to be the same sign. The second derivative with respect to x and the second derivative with respect to y. So let's write that down as the second important point. So the second derivative with respect to x and the second derivative with respect to y must be more than 0. Or sorry, need to be the same sign. And lastly, for it to be a maximum or a minimum, it depends on the sign of the second derivative with respect to x. Remember that the second derivative with respect to x actually determines the sign of the whole expression. If we go back up, we see that this entire expression is actually equal to just the difference between points Q and P. And remember, points Q and P is actually whether it's a maximum or a minimum, right? So if this entire expression that we have just painstakingly derived, so if this expression is a positive number, then we have a minimum. And if it's a negative number, it's a maximum. And what we have reduced this to is the first derivative, the second derivative with respect to x. And since it has to be the same sign as y, then, well, it's the same for both of them. Both of them would be either positive or negative. So if the second derivative with respect to x and the second derivative with respect to y are greater than 0, then we have the true minimum. Or the global minimum. In the same way, if the second derivative is less than 0, then it means we have the true maximum. So what we can do at this stage is a simple basic example to illustrate all of this pieces of information. But in a nutshell, just to summarize it, we have a true maximum. So what the first thing we should do is find the first derivative with respect to both x and y. And the points at which both are 0 will tell us the stationary point. So how do we know if either of those stationary points are a true maximum or a true minimum? We determine the second derivative with respect to x and y, and we also determine the mixed partial. We apply this inequality that I've just indicated, then that will tell us if it's a true maximum or a true minimum, if this inequality is greater than 0. And then after that, we proceed to check the signs of the second derivative, and if both are positive or negative, that will tell us whether it's a true minimum or a true maximum. We'll now consider an example in which we determine the stationary values and true maximum and minimum of a given function. So we'll consider the function z is equal to x cubed minus 6xy plus y cubed. So there's a different sequence of steps that we can follow to determine the stationary values and true maximum and minimum. The first of which is to determine the derivatives with respect to x and y. That is the first derivatives. We have day z dx, and that's going to equal to 3x squared minus 6y. And we set this equal to 0. And we do the same thing with respect to y. So we have day z dy is equal to well, derivative of x cubed is 0 since it's a constant. Then we have minus 6x plus 3y squared. And we set this to 0 as well. So we now need to solve these equations. These are simultaneous equations. And to do that, well, firstly, we'll divide this first equation by 3. So that will give us x squared minus 2y is equal to 0. And then we'll do the same thing for the other equation. We get minus 2x plus y squared is equal to 0. We can make y the subject of the formula in the first equation, and that will give us y is equal to x squared over 2. We can then substitute that in. We have minus 2x plus x squared over 2 equal to 0. That will give us minus 2x plus x to the power 4 over 4 equals to 0. So we can solve this quite easily. We multiply the whole equation by 4 and then take out x as a common factor. We get x into x cubed minus 8 is equal to 0. Solving for this, we get x is equal to 0 and x is equal to 2. We can now determine the corresponding y values. We know that y is x squared over 2. So 0 over 2 is just 0, and 2 squared over 2 is 2. 2 squared is 4. 4 divided by 2 is 2. So x equal to 0, y is equal to 0. And when x is equal to 2, y is also equal to 2. So we know that at the points 0, 0, and 2, 2, we have stationary points. So there are stationary points at 0, 0, and 2, 2. But how do we determine if they are true maximum or true minimums occurring at any one of these points? Or are they just local minimum or maximum? So to answer that question, we consider what's called the second derivative test. This is something that we had derived earlier. So use of this inequality that I am indicating here, that is the second derivative test. So we determine the second derivatives with respect to x, y, multiply them together, then subtract the mixed partial, and then we check if it's greater than 0 or less than 0. If it's greater than 0, it means that there is a true maximum or minimum occurring at that point. So we now determine the second derivatives. So the second derivative with respect to x, that will just be 6x. 3 times 2, and of course y is treated as a constant. Then the second derivative with respect to y, x will disappear, and then we have derivative of 3y squared, which is 6y. And lastly, the mixed partial. That's the second derivative of z with respect to x and y. So the first derivative is now being taken with respect to y. So we have 3x squared, so this will become 0 because we're now treating y as the variable that we are differentiating. And then we have minus 6y, and the derivative of minus 6y is just minus 6. So the second partial does not depend on either x or y. So we can now apply the second derivative test. And it is to check if the second derivative with respect to x and with respect to y subtracted from the mixed partial squared is greater than 0. So the mixed partial with respect to x, we consider first point 0, 0. So at point 0, 0, because that's our first stationary point, we substitute these values inside this inequality. So we can see that if we put in x in our second derivative, 6 times 0 is just 0, and it's the same with y, 6 times 0 is 0, and of course the mixed partial doesn't depend on either one. So we would have 0 times 0 minus 6 squared. The first term is just 0, and the second term is minus 36. So what this means is that this inequality is less than 0. So it means that at point 0, 0, there is neither a true maximum or a minimum. We now apply the same for the point 2, 2. So at 2, 2, we substitute these values in. Remember that the second derivative is 6x and it's 6y. So 6 times 2 is 12, and 6 times 2 is 12 again. So we're at the point 2, 2, and let's remind ourselves, second derivative with respect to x is 6x, so we're substituting 2 in here, so that's 6 times 2. And again, we're minusing 6 squared. So 12 times 12 is 144 minus 36. I mean, this is definitely greater than 0. So at point 2, 2, we do have a true maximum or minimum. How do we go about determining it? We just use the signs of the derivatives. You can just go back up. We see that if the second derivative with respect to x and the second derivative with respect to y are greater than 0, then we have a true minimum. And if the second derivatives are less than 0, then we have a true maximum. So now let's look at the signs of the derivative. We saw that the second derivative with respect to x was equal to 12, and this was also the case with y as well. Both are positive. What that means? It means that we have a true minimum at point 2, 2. And what is that value? All we do is we substitute 2, 2 inside our function. So this was our function, and we put in the values 2, 2. So minimum value of z is equal to x cubed, so it's 2 cubed, minus 6xy, 6 times 2 times 2, minus y cubed, that's 2 cubed. 2 cubed is 8, 6 times 2 is 12, 12 times 2 is 24, 8 minus 24 is minus 16. Minus 16, sorry, this was a plus here. Minus 16 plus 8 is minus 8. So that is our minimum value of this function. So in a nutshell, the procedure is as follows. The first step is to determine the stationary points, and the stationary points we get by finding the first derivative and setting them equal to 0, solving for x and y to determine the stationary points. And thereafter, we apply the second derivative test to establish if we have true maximum or minimums, or whether we have local maximum or minimums. And if the second derivative test shows that this quantity that I'm underlining here is greater than 0, then we have a true maximum or minimum. This was the case at point 2, 2. And then we check the sign of the derivatives to determine if it's a true maximum or minimum. And if we see that they're both positive, then we have a true minimum, which is what we established. And thereafter, lastly, we find that minimum value.